Greetings everyone, Professor Simon back with a brand new board, ready to do some calculus. Derivatives of inverse functions now. We're still in that chapter where we're adding more methods, more little laws and rules to help you get more efficient at taking a derivative really quickly. Inverse functions happen a lot, especially with a lot of our other types of functions like inverse trig functions, inverse hyperbolic functions, inverse of exponential and logarithm functions, things like that. Okay, so what we need to talk about here is just a generic method and a setup for being able to take the derivative of any function that happens to be an inverse of something you already know how to take a derivative of quickly. Okay, so let's start with the definition of inverse functions. If I have two functions, f of x and g of x, and they're inverses, right? Then f composed with g should give me the input value back, right? So it wouldn't really matter if this was x at all. This could be f of g of a. Then it would give me back a, okay? I'm going to leave it as x just because that's typically what we use for our input values here. But regardless, this is how you define inverse functions. If you can compose them and they basically eliminate but leave x behind, right, then they must be the inverse function of each other. Okay, so take this setup and then do the derivative of both sides, the implicit differentiation that we talked about in the last lecture, right? Doing so, the derivative of x just gives me 1. And on this side, I have a chain rule because it's a composition. So I do the derivative of f prime, leave g alone, times derivative of g, the inside, right? Okay, so then all I'm going to do is I'm going to divide this f prime over to here. And it may not look like it, but what I've actually been able to set up here is a derivative of the g function. Okay, so let's go all the way back to the beginning. Let's say we already know how to take the derivative very easily of some function named f. Come along down the road and we find out, oh wait, g is the inverse of f. Well, then that means the derivative of g is just the reciprocal of the derivative of f. But be careful, it's the derivative of f with the g function as its input. Okay? And that's part of the catch of doing the derivative of the inverse here, right? It is a reciprocal of the original function's derivative. Okay, so if they're inverses, you can expect inverses to have reciprocal slopes, but it has to be at special corresponding points, right? When two functions are inverses of each other, for example, if I've got just some graph of two functions, let's say I've got, f looks like this, and let's say that g is its inverse. Remember, to do inverse, I just take the line y equals x through the middle here, right? And I just do a symmetry around it. Okay, so let's say that's the inverse function g. The corresponding points that the derivative will be reciprocals at are the points where both functions have the input and output swap because they're inverses, right? So in other words, if I pick some value a for g, okay, then that same value of a is an output for f. Okay, they're inverses. They're supposed to be swapping these. Okay, and if that's the value that we're talking about being the input of the g derivative here, in other words, if I'm finding the derivative at this location here, then the slope of this tangent line right here, let me draw it this way. The slope of this tangent line right here will be the reciprocal of the slope of this tangent line right here. Okay, so these two lines will have reciprocal slopes. Okay, not negative reciprocal, they're not perpendicular, but just reciprocal at those particular corresponding points. Notice it's after I know which point do I want to find the derivative of the new inverse function. After I figure out what value that is, right, then that's what g of x is here, right? G of x is going to give me some output, right? G of x is going to be some, g of a rather, is going to be some output. We'll call it b. Then that same b value will be the input of f. Okay? In other words, the way this is set up, g of a is equal to some value b, and since they're inverses, then f of that same b value should give you a. Okay? And that's the corresponding points where the slopes will be reciprocals, one over each other like this. Okay? So you have to be careful. Instead of saying y's and x's, since these are two inverse functions of each other, it's very quick to get those y's and x's terminology confused. Say input and output for each of the functions, right? An input of f is the same thing as an output for g, and vice versa. Because they're inverse functions, that's what inverse functions do. They keep the same pairs, but just reverse their jobs, right? Outputs become inputs, inputs become outputs. That's what inverse functions do, right? So if I'm interested in the derivative of g at some special point, right, maybe at g of a, then if I'm going to relate that back to the original inverse function, I need to count that number that I'm looking for as an output of that other function. And then I'll need to figure out what that value is, what the other input is. Okay? And then that's what this is for. That's why this g of x is right here, right? Because you see g of a is b, and here's b. So g of a is basically there, right? Okay, so let's get an example here. I have a function, capital B of x is equal to x plus square root of x, right? And what we want to calculate is b inverse's derivative. See, notice the b inverse and then the derivative prime at the value 2. Okay? Don't say x equals 2. Don't say y equals 2. Right? It's real quick and easy to get those confused. Wherever the input of the inverse of b is 2. Okay? Okay, so if the input of the inverse is 2, then that means 2 could be considered an output of the other one. Okay? So let's keep all of that straight in our head. To begin with, what I'm going to need to do is find all of the input and output values that are working here. Okay? So, in other words, if 2 is an input on the inverse, then b inverse of 2 is something that I'm going to want to find. Okay? Because I want to know the derivative at a point, I'm also going to want to know the original value at that point, because that's going to go here, right? To do the g derivative at x, I also want to know what the g of x is, okay? But if I'm looking for b inverse of 2, then this is the same thing as saying 2 equals b of x. Okay? Because an input to an inverse is the same as an output to its original function, right? Because inputs and outputs reverse. All right, so right here, what that means is I'm going to be looking for the solution to this equation. 2 equals x plus square root of x. Okay? So I want to know the solution here. I'm hoping that you already see it, right? 1 plus 1, right? Because square root of 1 is 1, is 2. But let's say you don't see it. Let's go ahead and solve it. I'm going to move the 2 over. And I'm going to rewrite this as x to the 1 plus x to the half minus 2. And the reason why I'm writing it that way is because I need you to see that this is a quadratic structure, right? It's a trinomial, and the higher power is double the lower power, which means I can either use the quadratic formula or factoring. This one, factoring is pretty straightforward because I have two numbers that will add to 1 and multiply to negative 2. So that would be 0 equals something plus 2 times something minus 1, right? 2 times negative 1 gives me negative 2. 2 plus negative 1 is 1. What goes in the front of each of these would be x to the 1/2. Like this, right? Okay. So, when I'm going to solve this here is I'm going to split it. And here I'm getting x to the 1/2 equals negative 2. And here I'm getting x to the 1/2 equals 1. Okay. Well, real quick, how could a square root give a negative number if there's not already a negative out here? Right? X would have to be an imaginary number for this one. Okay? So this solution is no good. Right? It would have to be imaginary for that to happen. Okay? And we're not dealing with imaginary values here. On this one, however, this is just telling me that x is equal to 1. Okay? So, x is equal to 1 is the solution that goes with this, right? So let's reiterate what we've just found. We've just figured out that b of 1 equals 2, right, in this function here, which also means that b inverse of 2 equals 1. Right? Okay. Now remember, what we're doing is we're substituting b inverse there for the g here, right? F is the original function, b, and g is the inverse that I don't know anything about, right? Or don't know much about, okay? So g prime, in other words, b inverse prime at some value, I need to know b inverse at that value. And that's what we just found. Okay? So now what I need to do is take derivative of the original function. So I'll take the derivative of b, and then I'm going to do the reciprocal of it, and I'm going to plug in the appropriate value for that. Okay? All right. So I'm going to do my derivative. First I'm going to rewrite x plus x to the 1/2. Now b prime is equal to 1 plus 1/2 x to the negative 1/2. Okay? Or in other words, b prime of x is going to be equal to 1 plus 1 over 2 square root of x, like this. Okay? All right, so what I need now is to plug in the appropriate values and do the reciprocals, right? So here I go. B inverse prime at some value 2, right, is going to be equal to 1 over the b prime of b inverse of 2. Okay? That's what this is telling me. Okay? All right. So then from this formula, the value in question, b inverse derivative at 2 is going to be equal to 1 over, okay, so what's b inverse of 2? We know it's 1, right? And then b prime is this calculation here. If I plug 1, okay, which is this value here, right? That's just this. This is 1 right here. Okay? So if I plug 1 into this derivative here, I get 1 plus 1 over 2. Or in other words, 3 over 2. 1 plus 1 over 2, which is 3 over 2, and it's the reciprocal. So what I'm getting is 2/3. Okay? All right? Now, of course, the other way to look at this is I could have just figured out the b of 1 is 2 point corresponds to the b inverse of 2 equals 1 point. And remember, for corresponding points, inverse functions have reciprocal slopes. So b prime of 1, where I'm evaluating the original function, I will also evaluate his derivative. B prime of 1 was equal to 3 over 2. So then b inverse of 2 equaling 1, being the corresponding point, would have to have the reciprocal slope of that particular derivative point. Okay? So for these problems, the key thing is just to make sure that you're not getting x's and y's mixed up with inputs and outputs in your terminology. Make sure you're realizing that inverses use different terminologies for inputs. Technically, when you look at a function, all of them are x's and all of the outputs are y's, right? But then when you're trying to keep it straight, a y for one of them is the x for the other one. No. Input for one is the output for the other, and then you can, crisscross between inverses like that. Okay? All right. Just to give a visual side to this problem, let's go ahead and look at it here. Our function b of x was x plus the square root of x. Has this kind of bent shape right here. You can see it's more curved at the origin, sort of starts to straighten out, but it's always a little bit curved. The inverse of this function is not something you would have wanted to calculate just in your average everyday course, but this is what it ended up being. And don't forget, when things are inverses on their graphs, they are symmetrical around the line y equals x. So there's the line y equals x. You can see that they are symmetric around that line. Okay? Now, of course, the points that we talked about was we wanted the derivative of the inverse function when x is 2. So that's this point right here. I would like to know the derivative at that point. And what we calculated was 2/3. So notice the tangent line that I graph right here is in fact tangent, and it does have a slope of 2/3, right? Our derivative there is 2/3. But to compare it to the other curve, the original curve, the point 1, 2. So in the inverse curve, when x is 2, I get an output of 1. Okay? But on the original curve, the b of x, if I input 1, it outputs 2. So it's just what you'd expect. They have the inverse relationship there. And what I want you to notice is the tangent line at this point A on the original curve b of x is something with a slope of 3/2. Okay, so just as we were saying, corresponding points will have reciprocal derivatives on inverse functions. Okay, so if you have two inverse functions that are inverses of each other, and you find the pair of corresponding points, right? In other words, it's the same input and output values, but just swapped between the two inverses, then their derivatives will be reciprocals of each other, given if if all of the derivatives do, of course, exist. Of course, all of our limits and continuity have to line up. Okay? Okay, so now let's talk about one of the main reasons that we like to hit this section when we do, and that's because we need to be able to take the derivative of the inverse trig functions. The 6 main inverse trig functions come up almost as often as the actual 6 main trig functions. So we need to be able to take the derivatives of these. And also later on, these particular derivatives will make some of our antiderivatives easier as well. Okay, so let's start with inverse sine, okay, or also called arcsine, right? Inverse tangent is called arctangent. Inverse secant is called arcsecant. Okay, so just keep that in mind. I'm writing it with the inverse symbol here because that's sort of the theme of what we're talking about here. But you could just as easily write arcsine, A-R-C-S-I-N. So, I could go with the formula on these, but for me personally, it was easier to remember the rules on some of these after I worked through these processes for each one of these, just because of the way it forms. Okay, so here, let me show you what I mean. So y is equal to the inverse sine of x, and what that means is y is the angle and x is a sine value that goes with y. In other words, sine of y equals x. And you may notice that that's the way I have this set up here. The sine of angle y is equal to x over 1. And that could actually be for any quadrant. It's just I set it up in the first quadrant there. So sine of y is equal to x. Now take your derivative on both sides here. Do it implicitly. Remember, when we hit something with the derivative of y, I have to do it implicitly. Whoops. The derivative of sine y is going to be cosine y and times dy dx, right? That's our implicit chain rule there. And of course, derivative of x is 1. Then, if I were to divide both sides here, I would find out that dy over dx is equal to 1 over the cosine of y. And that should make sense to you because that was the setup that we would see from the formula in the last scene, right? I would have the derivative of the original function, the sine, of the y value, of the inverted value, right? Okay, so cosine of y, how does that relate to sine of y over here, right? If you look at this triangle, if I were to solve for the missing side over here, right? The missing side underneath here, using Pythagorean theorem, should be the square root of 1 minus x squared. Right here, if I solve for that, okay, let me, I'll show you the long way. I have 1 squared is equal to x squared plus something squared, right? That's how I'm getting this piece right here. So if I were to subtract, I would have 1 minus x squared is equal to whatever that something is squared, right? So then, of course, if I square root both sides, and remember, I'm keeping it positive in this case. I could have done either way, right? It just depends on which quadrant you're talking about. And you got to be a little careful, right? Because technically, arc sine is really only going to be yielded for certain quadrants anyway, right? Okay. So anyway, my point is the cosine of y here is going to be equal to the adjacent over the hypotenuse, right? But it's 1 over that. Okay? So then what I've got is that the cosine of y here is equal to this over 1. the square root of 1 minus x squared. So my derivative dy over dx of the original arc sine is equal to 1 over square root of 1 minus x squared. Okay? Now I want to add, there is another way you could have gotten to this right here. From the sine y is equal to x, right? If I were to square both sides, I would have x squared is equal to sine squared of y. And don't forget, sine squared of y is equal to 1 minus cosine squared y. And then I could easily solve for the cosine y, and I would get this same thing by using my Pythagorean identities from here. So you can do it graphically, or you can do it with the identities. I'll show you in the next one using the identities, so you'll see both ways. Okay? So let me write down a generic rule here. The derivative of arc sine, I'll go ahead and write it the other way, is equal to 1 over square root 1 minus x squared. Okay? Now let me add a little something in here. The derivative of the arc cosine of x is equal to the negative of 1 over square root 1 minus x squared. You can do this one the same way as I just did the inverse sine, and the only reason the negative pops up is because of the co, right? Derivative of cosine is negative sine. I probably said this before. Whenever you take your derivative of something with a co in it, you're going to end up with a negative of something, right? Okay, so here are two of those derivative rules that you're going to want to remember. The derivative of arc sine, the derivative of arc cosine, the derivative of inverse sine, the derivative of inverse cosine. All right? Okay, next. Section this off here. Let's go through the same format, right? I'm going to say that tangent of y is equal to x, right? That's how inverses work. Tangent of y is equal to x. So therefore, if I take derivative of both sides, derivative of tangent of y is secant squared of y times dy dx is equal to 1. So then dy over dx is equal to 1 over secant squared y. Okay? All right. So then how do I get from here to here? Well, notice again, tangent and secant have a Pythagorean relationship, right? So right here from this statement, if I just go over a little bit and notice that if I square both sides and add 1, so like this, tangent squared of y is equal to x squared, right? Add 1 to both sides, plus 1, plus 1. Tangent squared of y plus 1 is equal to secant squared of the same angle, the y. Okay? So what does this mean? Well, secant squared right here is equal to x squared plus 1. So 1 over x squared plus 1 here. Do you notice a theme here? We're starting with these inverse trig functions, but then the derivatives that we're ending up with are not trigonometric at all. Kind of feels weird, right? Okay, so then let's write the rules down right here. I've got my derivative of arctangent of x, the inverse tangent of x, is equal to 1 over x squared plus 1, right? What do you think the derivative of arc cotangent is? The derivative of arc cotangent of x. What do you think? Just like the same pattern as before, right? Negative 1 over x squared plus 1. So now I've got those two. right? Okay. So I've got these two inverse trig functions done. What about that last one? Arc secant, right? Okay. So here we go again. Same pattern as before, right? I'm going to do secant of y is equal to x. I'm going to take derivative of both sides, which derivative of secant of y is secant of y times tangent of y times dy over dx equals 1. And again, I'm going to divide it. So dy over dx is going to be equal to 1 over secant of y times tangent of y. Well, we already see that secant of y is equal to x. Now right here, I'm going to be a little bit careful, okay? I need to start being a little bit careful with the secant here because the sine and the tangent over here were odd functions and they worked kind of differently, okay? But right here, if I were to actually plug the y into here, I would be doing the secant of the inverse secant, okay? And because of the quadrants that we define some of the arc functions with, what I'm actually going to get is, instead of just secant y equaling just the x here, for this one, for just this first piece, I'm going to get the absolute value of x, okay? Same way a lot of times that we get the square root of x squared is absolute value of x, right? Whenever you do something like this with an even function, you've got to be a little bit more careful. So I'm going to get from secant of inverse secant, right? I'm going to get absolute value of x from that secant of y. Now what about the tangent of y, right? Well, that's going to be very similar to what we did over here. I've got that secant of y is equal to x-ish, right? So I'm going to use that to manipulate here like we did over there. And if I square both sides, so that would be secant squared y is equal to x squared, right? Okay. That sort of takes care of the absolute value right there anyway, right? If this was absolute value of x, squaring it would sort of make it all balance out anyway. Now, if I subtract 1 from both sides, secant squared y minus 1 is equal to x squared minus 1. Secant squared of y minus 1 is equal to tangent squared of y. That's your Pythagorean identity. Like this. Okay? Now I just take the square root of both sides. And again, you'll notice I'm picking the positive. That's also having to do with the quadrants that these things are designed for. Okay? So I'm getting a square root of x squared minus 1 for the tangent of y piece there, right? Tangent of y is equal to that. So let's write our rules down. Derivative with respect to x of the arc secant of x is equal to 1 over absolute value of x times the square root x squared minus 1, and derivative with respect to x of the arc cosecant of x, of course, would just be the negative. Like that. Okay? So here we go. You now have 6 more derivative rules that you need to know. These are functions that come up often enough that they need to be given their own little space of, okay, I know the derivative of that. Just like we know the derivative of tangent of y is secant squared y, right? Just like we know the derivative of sine y is cosine y. You need to know, oh, the derivative of arctangent of x is 1 over x squared plus 1. Okay? These are just 6 more of the rules that need to come up all the time, and they need to be just sort of drilled into your head. I don't mean drill as in zzz, I mean drilled as in, you know, working out the drills of practicing them. Okay? All right. So, these are the rules. Now let's go try a few examples practicing with them. Let's finish up with some examples of the derivatives of these inverse trig functions, right? So, let's start with f of x I've got over here. The quantity 4 plus inverse cotangent of x, all raised to the 5th. Okay? So, I'm hoping that you're seeing the chain rule that's going on here, right? I've got an inside quantity raised to the 5th power. Okay, so let's do our derivative. F prime of x is going to be equal to 5 times 4 plus inverse cotangent of x to the 4th. So remember, chain rule, I did my outside derivative, right? Brought the 5 down. 5 minus 1 is 4. And then I'm going to multiply by the derivative of the inside, right? So the derivative of the inside function here is 0 plus, and then the derivative of the inverse cotangent. So times negative 1 over x squared plus 1. Okay? So we could write it a little bit more concisely. Negative 5 times 4 plus arc cotangent to the 4th, all over x squared plus 1. Okay? Next, I've got g of x here, which is x times the arcsecant of x plus the square root of 1 minus x squared. So then, what I want to do here, of course, with the plus sign, is do the derivatives of these separately. And noticing that this, of course, is a product rule, right? Because of the multiplication here. So let's begin. G prime of x is going to be equal to, I'm going to take the derivative of the x, leave the arc sign alone. So that's going to be arc sine of x plus, right, because derivative of x is 1, plus, leave the x alone, times derivative of the arc sine. I've got 1 over square root of 1 minus x squared. Plus, now I've got to do the derivative of this, okay? Don't forget, the function here is really just this to the 1/2, right? Okay, I'm going to leave myself a little space here. I'm going to drop the 1/2, leave the inside alone, subtract 1 from the power, and then times the inside derivative. So I have times negative 2x there. All right. Now, of course, the arc sine of x, that's not really going anywhere, right? G prime of x. I've got arc sine of x. Plus, now this is just x times 1. I've got x over square root 1 minus x squared there. Plus, no wait, minus, now look at this, 2 times 1/2, right? 2 times 1/2 is going to reduce, and I'm left with the negative 1. X. This is a negative power, so it's going in the denominator, and it's a 1/2 power. So notice it's the square root of 1 minus x squared. Okay? Double check. Look again. Look. Negative 2 times 1/2 gave me the negative 1 here. The x is still in the numerator, just because it's an x multiplied in. The negative exponent, put this in the bottom. The 1/2 power is the same as the square root. And again, the only reason I bothered converting was because I noticed it would be very similar to this. In fact, it's practically identical, isn't it? These two are the same, and I'm just, one is positive, one's negative. They're going to add out to 0, right? This right here is going to always add out to 0. So my derivative here just happens to be the arc sine of x. All right? Sometimes that can happen if you mix together the right functions, and then product rules and quotient rules bring out all of these varieties of pieces flying all over the place. It's possible for some things to combine and be simpler things, or even combine and wipe out. In this case, it happened to simplify out. All right, let's do the derivative of this guy right here. H prime, right, of x is equal to, I've got 7 times the inverse secant, and the inverse secant has something in it, right? Okay, so what I'm going to do is a chain rule here, which means I need to do the derivative of the inverse secant first, and then I'll multiply later times the derivative of that inside piece. Okay, so let's do it one thing at a time. I'm going to have 7 times the derivative of the secant, or I'm sorry, the inverse secant is 1 over the absolute value of the inside piece. Okay, well, the absolute value of the square root is going to be itself in this case, because that square root's going to always put out positive values. But I'll write it for the first step here, like this. Okay, so there's the absolute value of the x, the thing that's on the inside, times the square root of the thing on the inside squared. Okay, so that's square root of 3x plus 1 squared minus 1. Okay, so far all we've done is the derivative of the inverse secant times, now I've got my chain rule kicking in, the derivative of this. Well, don't forget, this is just something to the 1/2 power. So his derivative is just going to be 1/2 times that inside piece to the negative 1/2. But wait, that was a chain rule too. It was another inside function. The derivative of now the 3x plus 1, I have to do times 3. So I actually had 3 composed functions, right? I had the arc secant, I had the square root, and then I had the 3x plus 1. Okay, so that's a double chain rule there that we just performed. Let's regroup. I've got h prime of x here is going to be equal to, I've got 21 on the top, and I'm going to have just a free-floating 2 on the bottom, right? So here we go, big old fraction here. I've got a 21 up top, and that might actually be the only thing up top. Looks like it. And I've got a free-floating 2 on the bottom. The absolute value of that square root is just that square root again. Here, notice this is a square on a square root. That's just going to be 3x plus 1 minus 1. Like that. Okay? I already took care of the 1/2. There's the 2 there. This is negative power, and it's a radical in the denominator. Square root 3x plus 1, like that. Okay? I'm hoping you're noticing that these two things are the same thing, and I'm multiplying them, right? I'm getting a squaring of a square root. Wait a minute, be careful. Squaring a square root, or the square root of something squared, is not just a wipeout, right? I'm going to be extra careful here. Squaring with a square root of a generic function, I'm going to get 2 absolute value 3x plus 1 like that. And then notice right here, I'm just going to have the square root of 3x. Okay? All right.